Dean Sridhar sir, how are you?
Yeah, fine, fine. Very good morning,
Good
madam.
morning.
Honestly, madam. Good morning, madam.
Good morning,
Okay.
sir. How are you all?
Yeah, I'm happy. Really, I feel happy in seeing in online also, and for your readiness in accepting our invitation also in this AGSC conference, the two student-friendly conference. So your participation as an alumni of this university is highly solicited, and the today's conference theme is food formats and future, envisioning amazement of yield generating and nourishing food. So here we had, I think, 10 things. In the 10 things, the theme allotted for our agricultural engineering is trends in agricultural engineering for the changing landscape. So in this theme, I think both of you have been invited for delivering the guest lecture. So first of all, on behalf of university, I extend my heartfelt thanks for accepting our invitation and sparing your valuable time in delivering this presentation. I really am happy and really I congratulate both of you for your attachment towards this engineering college as well as to this great agriculture university. That too in these golden jubilee celebrations. Thank you.
Sure,
First,
thank you.
let's welcome Dr. Venkatramana Sridhar to deliver water management impacted by climate extremes and food, energy, water nexus. Thank you, sir. Please welcome. Please.
Sure. Thank you. Thank you, Dean Dr. Sridhar. Appreciate your kind words and thank you for your generous introduction. Thanks to CAE faculty members who are present there and also for the students. I feel always happy to talk to CAE, faculty and students. So that's my pleasure, and I really appreciate your giving me the opportunity to talk to all of you. So should I get to the topic of presentation directly? Can I go ahead and?
Yeah, please,
Okay.
please.
Okay. So I will share my screen now. Can you see my screen?
Yeah. Please put slideshow. Yeah.
Okay, 1 second. How is this? Can you see?
Yeah. It's good. You proceed now.
Okay. So welcome to my presentation. So I will take about 30 minutes, 30 to 40 minutes, and I'll be open for questions during the presentation or after the presentation. So the topic for today's presentation is water management impacted by climate extremes and food, energy, water nexus. My name is Venkatramana Sridhar. First name is Sridhar, and Venkatramana is my father's name. As we expand our initial, it became my first name here. I'm an associate prof in the Department of Biological Systems Engineering at Virginia Tech. My former affiliations include University of Washington as a postdoc. Then I was in University of Nebraska, Boise State. I got my PhD from Oklahoma State. I'm also a professional engineer in Idaho and Nebraska and diplomat of Water Resources Engineering Society here. Conduct research in the impact of climate change, hydrology, water resources, sustainability, and systems dynamics. Includes water supply demand management. Currently advising 4 graduate students to postdocs. I teach 2 courses on an average, but I'm fortunate not this semester that I'm teaching these classes. External collaboration includes several colleges here in the US and also in India, including IIT Kharagpur and Madras and the lower Mekong River Basin countries, including Thailand, Laos, Cambodia, and Vietnam. I'm a member of several professional societies. I'm also a Fulbright Fellow of this year. Let me get to the topic of discussion today here. I just want to start with this presentation or the initial slide to show the extent of problems that we have right now. This is a little bit of a dated slide, but we have all kinds of extremes, not just for 1 year that I show, but it's been happening many times every year now in many places. Drought, heat, fire, floods, high precipitation, cold, and air quality issues. You can see on the global scale, you have this problem present almost in every continent and every country. And if you look at specifically Asia, extreme heat that we are seeing repeatedly during the summertime, and the area that's actually impacted by this extreme heat is also increasing year by year because of temperature increase, general warmer conditions that we have. Number of warmer months for any given year is increasing from anywhere in India all the way up to China, Russia, in Japan, Korea, and all the other Southeast Asian countries. And the area fraction, when you look at it in percentages, also it's quite high. Number of events per year is also becoming higher every year. So again, these problems are, while we say these are general, there are also location-specific issues. So what we looked at in one of our recent study is to see how the precipitation climatology or the water availability issues that will change by river basins and also by locations. One such study actually looked at different cities in India and looking at how these trends are changing in the last 115 years or so, from 1901 basically to 2015, 115 years, and use that information to see how that will be informing us to project into the future. One such projection is looking at how drought will be characterized. And again, these are based on observational studies. And then into the future, we looked at different scenarios of climate models from 2010 to 2039, 40 to 69, and 70 to 2099. All over India, if you see the drought duration on the left side and drought occurrence on the right side is on the rise. Duration is about 4 months, and the occurrence of events anywhere from 100 to 160, you will see into the fag end of the 21st century. So that is kind of a scary situation, but of course, you need to have an idea about how these things are changing into the future to do a better water management planning and strategy. And then when we looked at the historic conditions for climatology, coming close to the same previous slide that I show here, annual rainfall, monsoonal rainfall, 1-day rainfall, and 10-day rainfall that we are seeing for different cities, the signature is kind of mixed. As you see, in some cities, you are looking at annual rainfall totals are increasing, but monsoonal rainfall, if you look at, we get roughly about 4 months or so in a year, which is also changing in some places. Where you have general increase in annual rainfall, your monsoon rainfall is also increasing, and where it is decreasing, you see a decrease in the monsoonal rainfall. And 1-day maximum rainfall and 10-day maximum rainfall is another indicator people are using nowadays, because with all these infrastructure that are in place, if you have increased 1-day precipitation, is it going to be sufficiently accommodating these high amounts of rainfall? And what is happening with 10-day rainfall? So if you look at many cities are really having increased 1-day rainfall and 10-day rainfall, and that's going to have actually a problem. You may have actually the same amount of annual rainfall for those places, but if they come all at once in a week or in 1 day, that is not going to help us plan for a better water management strategy. And looking at the river basin scale also, what we are seeing is trends in 1, 2, I'm sorry, this is 1, 2, 3, and 5-day maximum rainfall is changing in the historic times. Here we divided them into 2 windows, 1901 to 1970, 71 through 2015. Again, the red color indicates that we are seeing the magnitude as well as a number of events that are changing on the left side, and the annual maximum is also changing. 1 day, 2 day, 3 day, 5-day maximum precipitation amounts are increasing in many river basins. So in India, I think, as we all know, rainfall comes always in heavy quantities. Unless we really have a better management in terms of storage and utilization for multiple sectors, we end up in shortage. That is not just the case for India. That is very much true in another basin that I'm going to be talking about a little bit more in depth, which is the Mekong River system that I've been studying for the last 5-6 years now. This is an interesting river basin that I wanted to introduce you to all of you. It starts in China and then flows a little bit from Myanmar, and then the four major lower Mekong countries we call Laos, Thailand, Cambodia, and Vietnam. And it drains, it finally ends up in the South China Sea. It's a 4,500 kilometer long river, upper Mekong and lower Mekong roughly dividing somewhere in the middle here. And the problem that we have right now is we have seen increased number of dam projects in this basin. Every year, roughly, they build about 20 dams. Roughly, on an average, you have about 450 dams in the last 30, 40 years they have built. So this river is heavily dammed. So the flow is actually arrested and flow is decreasing downstream. And that's posing some other problems that I will touch on later. This basin covers about 60 million people. They rely on this river. If there is no flow, it is affecting the livelihoods of different population here in all countries. And many of these farmers and people in this area rely on this river water for irrigation and also for fisheries. So now I'll focus on the lower Mekong because that's where I think we have heavily populated regions, and there is also new projects that are coming more in number, like Laos and Cambodia. They plan to build dams, but they are also having extremes like drought conditions and drier seasons from November through April. So one way of looking at it is if they build dams, they can actually avoid drought years. For instance, in the last 20 years alone, they had severe droughts in 90s and also early 2000 and as late as 2015 and 16, they had severe droughts. So what we wanted to do is, can we predict droughts? Can we help farmers to understand how to manage water during these periods and how can they increase their food production and also at the same time not affecting too much on the energy production side. So I'll talk about these locations where we try to extract information about drought conditions. For instance, one of the widely used index is called Palmer Drought Severity, or PDSI. This is a global data product that we can easily extract for different locations. What we did, we extracted the coarse resolution data from this neighborhoods and then extracted model produced soil moisture and then tried to compare the PDSI derived from soil moisture based estimates and also from these global products and tried to compare for different locations, different selected watersheds. And what we are looking at is there is a good agreement between what was produced on a global scale and at the local scale when we try to extract information and provide into the derived product like MPDSI. And one of the important factors here is this drought relates to precipitation, temperature, evapotranspiration conditions. The anomalies that we are looking at, seasonal conditions are on an average, long-term average anomalies. The soil moisture index that we have here, SSI, versus all this precipitation, temperature, evapotranspiration, they pretty much correlate well with each other. So in other words, if you know little bit about precipitation, temperature, and ET anomaly, and then derive any drought index, then we are able to match the conditions with the real world scenario of drought that occurs in this region. 2015 versus 1992, we are able to capture the difference. 1 year you have severe drought in all the places. In another year you don't really see. That is actually represented from these anomalies also. That is derived from both field data as well as from the model. How is it useful? we are actually extending that kind of understanding into looking at yield reductions or yield loss between drought and non-drought years into the future. This is at the provincial scale. In other words, in Indian context, I would say these are districts. There are about 70 provinces that we have, in 77 or so provinces in this area. We are extracting global models and looking at crop yield loss that we have, between drought and non-drought years. In some places, you don't see a big loss. In some other places, you have increases in loss or yield difference, reduction in yield that we are expecting. So what we then did was to revert these conditions into how much area they should be irrigating and what is the percentage that they have to irrigate between scenario RCP 4.5 versus 8.5 here from different models in order to minimize the food production loss. If they want to really maintain what we produce as of today into the future, how much water they should apply, what areas they should be focusing in on. So this, understanding was necessary for country level water resources planning and management. When I look at the numbers, Cambodia, Laos, Thailand, and Vietnam for different basins and different models, there are some countries, I don't mean to overwhelm you with all these numbers here. If you just look at the ones that are in red color, red fonts, what we are seeing here is some countries have less room for increased irrigated areas, whereas in some countries we have room for expansion because of the projects agriculture production that they have to maintain. Why Thailand is low is because it's already heavily converted region for irrigation. And Vietnam, in some areas, they are really affected because of lack of water. In some places, they are needing to expand into the future to minimize food production loss. So that's the takeaway from this slide. When we look at, one other thing we normally tell about water stress between drought and non-drought year and how that can impact rice yield, that is pretty much, very unpredictable, right? As you can see here, rice yield correlates with, some, amount of prediction in drought conditions, MSDI, the stochastically derived drought index that we have here. When you have, the yield is less, and the same year is, of course, drought is actually affecting the region. So high year means, of course, you have higher yield means you have low drought problems. So that is pretty much understood, on an average. But how do they differentiate between a drought year versus non-drought year? If you look at by decades, the reduction in yield is quite substantial in non-drought, in drought years compared to non-drought. Non-drought is blue bars and drought year is red color. So there is some level of decrease that we see in the future during drought years, which is obvious. But the main thing is, what are the areas that will be affected by drought? How much water they need for irrigation, and how can they maintain the same level of productivity is the one thing that we wanted to really look at. And we wanted to predict that, expanding into both near term and also for the longer, projections in a longer period into the future. We were able to do a reasonably good job with different indices that we derived for different locations for the entire the Mekong region. What we found out is, of course, whenever we talk about forecasting in a shorter time period, the agreement is good in the first 2 months, and then it falls apart, meaning you cannot predict what will happen beyond 2 months in the seasonal forecasting window. And that is going to help, improve our understanding based on newer products, newer models, and also, tightening some of the uncertainties that we have in this area. Why do we need to understand drought? Primarily is to really look at it in the context of food, energy, water nexus, what we are, like I said before, this basin is impacted by all these dams. So we look at the river with all these dams in a series. Basically, they are cascade of dams that we have from the system. So we look at how to optimize these reservoirs from different conditions. So I'm just showing you quickly a bird's eye view of how we implemented the model. The same water is used for hydropower, irrigation, municipal and industrial purposes within the river basin by each country. But there is always a conflict for this limiting resource, water resource in this case. So how do you divide them? So in a framework like this, what I'm showing, we try to really look at the total supply, and we also look at the demand side, and how can we optimize the power in the hydropower production versus area for increased irrigation, and how do we really provide water for municipal, industrial, and drinking water supplies for urban areas in the basin. So we built this in the systems dynamics framework, and then looked at all of the projects together, multi-purpose dams, irrigation dams, hydropower dams, and see how their behavior is changing from past into the future. We are seeing pretty much the reduction in some cases for irrigation dams and multi-purpose dams, and hydropower dams have some, both good and bad news. Good in the sense they have a chance to increase their production in some project sites, but there is also reduction in some other locations. Coming back to the US here, this is one of the widely used slide that I wanted to show you. US has a distinct variability by region. For example, where we come from, both of us, myself and Dr. Anandi, on the eastern side, you have increased precipitation potential, or historically also we have seen quite a substantial increase, up to 71% in the New England areas. In the eastern, southeastern area, 27%, whereas in other parts of the US, you have a moderate increase in precipitation. Why does it matter? Like I said before, these are impacting our day-to-day activities because the economic conditions are impacted by these extremes. As a matter of fact, last week we had a big hurricane that crossed our tropical storm, Ida, that crossed northeastern region, and ditto of these conditions, economic disaster and closing down of the airports, and cities were shut down, and all of the problems relates to severe weather and extreme conditions. One other project, or the small project that we did on the eastern side here with the coastal cities that are vulnerable for sea level rise and flood problems, is in my own state, which is Virginia, close to Washington, D.C. All these cities are impacted by extreme precipitation events. We looked at by cities how things are changing from the past. The red lines of intensity, duration, frequency graphs that you're all familiar with as engineers, that is pretty much fixed for the historic times, but that is substantially changing into the future for 24-hour versus 48-hour rainfall amounts, similar to what I showed you before for India. So what we are seeing, though, this increased amounts of rainfall, 100-year events coming in 10 years, or 500-year events coming in 100 years or 25 years. These are really causing problems for existing infrastructure in place. Norfolk, I'm not sure if you're able to see this, it's one of the main cities on the East Coast for US naval fleet. They have parked about 17 aircraft carriers on this coastal town here. Basically, because of sea level rise, this is Atlantic. The sea level rise that's happening because of the glacier melt and ice sheets melting in Greenland and above is actually causing substantial increase in the sea level rise. And because of increased rainfall on the land and storm surge, meaning when the hurricanes cross, they bring lots of seawater into the area, creating a compounding flood problems in these areas. And that is, concerning the security assets of this region. So we want to really understand how to maintain or manage, these areas when it comes to water resources. I'm actually showing this blank slide, to show how each of these locations are going to be impacted when you just look at it in separation or in isolation from the other versus how you look at it in an integrated way. I'll just populate these slides quickly here to show you the interconnectedness of different water related sectors. And you cannot isolate them, you cannot see them individually, you have to see them together. So that's the message I wanted to convey here, looking at the collection of different dependent interconnected areas that we should see as engineers. This is the day and age of interrelated interdisciplinary kind of research that we wanted to see, and that is needed for local scale, that's also needed for national and international basins, particularly like the Mekong system that I showed. And my area is actually looking at all of these things combined in from global climate models to hydrology, groundwater models, and link them to extract as much information as possible based on what we know from the limited data and see how we can project into the future. So that's the broader part that I wanted to show you here. Not sure how much time I have here now, probably another 10 minutes or so.
You can take some time, Sridhar. Mine will not be so long.
Oh, okay. So then what I did, of course, these are our students' work here. I'm showing, highlighting. I'll skip some slides because I talked just about publication importance, to our audience sometime recently. But I wanted to also talk about how we take advantage of the data that's already available from different locations within the US. One such paper that we came up with was using site-specific soil moisture data and then looking at in the context of hydrology models and wavelet analysis. The reason why we did that was to show the combined effect of both stochastic and physical modeling is required to understand the existing data that we have, and also how can we improve our understanding on drought. In this case, we looked at different models that produce soil moisture information and then look at the areal extent of drought from aggregation of the soil moisture indices from 4 weeks to 8 weeks, and see whether or not we are able to capture these severities. And in the US, 2000, 2002, 2006 to 9, 11 to 12, we had severe droughts, and we were able to pretty much capture well with 8 weeks of aggregation of soil moisture. And then we relate that with ground truthing of data that we have from US drought monitors. This D1 to D0 to D4 shows the extent of drought. This is abnormally dry versus exceptional drought, which is the darker brown color that we have. Large areas in the US are constantly subjected to drought. When it comes in a big way. So that's what we saw historically, and we were able to actually relate those with the models, a combination of both models and stochastic approach. And then we wanted to really see how we extend our understanding from seasonal forecasting into long-range projections. Just quickly jumping the topic here a bit, I wanted to show you on the national scale how we divide the country into smaller pixels of 25 by 25 kilometer, and then look at model-derived soil moisture-based drought index. In this case, we are showing SWOT-derived soil moisture-based drought index versus variable infiltration capacity or WIC model-derived soil moisture indices. And you can clearly see majority of the countries, let's say, you just pick this 2013 scenario from different models, it pretty much captures the observed conditions on the ground with these models. So we are pretty much able to convince ourselves that these models are doing a good job in terms of providing reasonable estimates of soil moisture under drought conditions, which can be used for mapping drought conditions on a country scale. That is the message that we can take away from. And even on seasonal scale, like I said before, there is some improvement needed when it comes to precipitation, but temperature-based models are really good. What we are seeing here is 6 months to 9 months forecast of precipitation temperature that can be useful, but they are not all that useful beyond 2 months. If you want to predict drought, based on the projections that we have or forecasting data of temperature and precipitation, for the first 2 months, they really do a good job. But beyond that, the data does not really have much meaning because precipitation is hard to really predict into the future. And one other watershed that I wanted to cover here is this Chesapeake Bay watershed, which is in this map you see in blue color, close to National Capital Region, Washington, D.C. And of course, it has 5 or 6 different states in this map, starting from New York, Pennsylvania to Virginia, West Virginia a little bit, and then Maryland, and then it drains into the Atlantic. There are many sub watersheds that we have here. The same issue that we saw on the national scale, we are able to really see on long-term historic conditions, many years of drought that we have. And we looked at the anomalies in precipitation and temperature. We are able to see substantial change into the future, meaning less precipitation in some regions, more precipitation in other regions. You can see a decreased precipitation of 5% to increased precipitation of 10% in different locations. So we have to really take away from here, what we have to take away from here is the local scale variability that we need to accommodate when it comes to floods or droughts. And high resolution modeling is, of course, one of the important element that we have to consider. Different models provide different things. When we look at 4 different models here for near future versus far future conditions based on soil moisture derived from WIC model and SWOT model, you see the colors are changing so widely. In some places, model S2, for example, is producing extremely high drought conditions compared to another model. And how do we then go about making decisions based on these models? That's a confusion that we have. But even to address those uncertainties, people have come up with ensemble averages and looking at how we can really integrate them together. So this slide I have already covered before. Basically, we look at different cities, different localities, and see how precipitation pattern is changing. Now, why are we looking at all this at a local scale? Of course, they have some connections for communities, but when you look at it from the global perspective, this urban water security coming from surface water deficit and also from groundwater conditions that we have here on the left panel shows that, of course, whether it is India or the US, we have big problems of both surface water and groundwater conditions. And extrapolating that to cities, in the top 20 cities, you have Chennai, for example, in Tamil Nadu, that we have in many cities in the US and some cities in North India, like Jaipur. We are going to see a problem in the next 50 years or 30 years. As a matter of fact, in 2050, urban water deficit problems. So these studies are really important for us to know how critical water is going to be. In Chennai, for example, during drought times, when there is low monsoon rainfall, we already start seeing water being supplied by water trucks. And how can a city survive, being fed by, these water trucks? So that is a question that we have for engineers today to understand what can we do, what can be done to improve our water management practices to make sure that Chennai or many other cities in South India, for example, are waterproof or water safety conditions that we will have into the future. Switching gears a bit here, I wanted to show you one last part of the project that I wanted to discuss. One is this Idaho region where we have irrigated agriculture. It's a dry region, not much water for agriculture, but people tap both groundwater and also water stored from this river system in the reservoirs. There are about hundreds of projects that we have similar to the Mekong River system, that this actually served as the test bed for my systems dynamics modeling framework that I did for the Mekong system recently. What we did was to look at, this is Yellowstone National Park, which is one of the world famous natural national park system that we have in the US here. And water flows in the river from this direction, from east to west. There are dams that block the flow, and they are used for hydropower. They are also used for irrigation. Ditto, similar condition that I showed you for the Mekong system. But again, this particular system is so operated well that people here in this basin are able to meet multi objectives here in terms of hydropower, irrigation, flood control, and fish flows. Basically here they have to consider certain amount of water to be left in the river for environmental conditions, for aquatic habitats. So they meet those objectives. We did that in integration with a surface hydrology model, with a groundwater model. I'm a process modeler, so I looked at how to improve the model predictions. Existing models don't have certain processes defined. For example, this variable infiltration capacity model, widely used around the world, don't have groundwater component in it. So we tried to integrate another model called ModFlow, which deals with extensively groundwater systems, and connecting these two together, of course, in an integrated way, took a lot of effort, but we were successful in demonstrating that we can do it. The main reason why we do that is because this particular basin, the Snake River Basin that I showed you before, has a lot of groundwater underground. Like this is a big, huge reservoir of lake storage underground, and people take this water for irrigation, for all the other needs. But again, if they don't manage it properly, their water table is going down. That is what is happening in many river basins in India also. Particularly for the Snake River Basin in early 1900s to 2000, if you see, area of irrigated agriculture is expanding, and water is actually extracted from both groundwater and also from surface water. But unless they manage this system effectively, they will have drawdown in the aquifers. They're also going to have problems for irrigation, for raising crops. In summary, I wanted to say, a couple of things. One is, for obtaining reliable precipitation for droughts and floods in the future, for reliable predictions of floods and droughts, you need to have reasonably good precipitation, estimates or data products. Monitoring is good. We want to really look at data collected from the field, but of course, modeling is essential because we cannot really look at field data for every location. So some places you need to still rely on these model produced estimates. Even in modeling, you need to have a combination of both physically based models and also statistical approach. A combined approach is required. And when you look at it from both long-term projections and also for short-term forecasting conditions, there are models that do a good job for short-term conditions. They're not good for the long term. And same way, some products are good for estimating shorter period forecast, but some models and data sets are needed. Different models and different products are needed for long-term projections. So you need to understand that for a given location. And then irrigation water requirements to compensate the loss of crop yield is possible, which is what we demonstrated for the Mekong system. You need to really understand how much water is needed to minimize crop loss during the drought years, especially. And again, how much water can be stored in the existing reservoirs, and how do we really avoid food security concerns, especially during the dry season. And drought analysis provides a framework for resilience assessment in the context of food energy nexus. And my final thoughts are these following. Basically, large-scale hydrological assessment for water security and sustainability needs good data, models, and actually combining them together to draw some conclusions based on those. So this is essential for our understanding to improve better, to have better water management strategies. And climate change at a local scale is required. Of course, it can help farmers, it can help people who manage water, and again, for infrastructure. Sustainable agricultural management is to be considered at the system level. Again, you have to look at it from the local scale perspective, but you have to see from above, from a large area perspective, and how each of these systems are connected, and one, when you disturb, how the other one is affected. That kind of connectedness we want to establish at the systems level. And we as humans are causing changes to this Earth system. And how can we really look at it from the coupled modeling analysis perspective? And that's again required if you want to have a better understanding for floods and droughts, and also for better water management strategy, especially in the future during our, the changing conditions because of climate that we have actually caused as humans. So that we need to really understand how we can quantify and accommodate them in our estimates of droughts or floods for better water management. So with that, I will stop my presentation. Thank you for listening. Appreciate it. Thanks.
Thank you, Dr. Venkatramana Sridhar, for your excellent presentation and very beautiful slides and subjective slides, and slides presentation is excellently good. Really, we were much benefited because of your involvement in presentation, one thing. And second thing, we could able to understand the importance of water management, that too due to this climate change. In fact, in India, lot of things have occurred because of the climate change, and nobody had given this much thought-provoking lecture. Thank you, really, Doctor. Really, I am proud of you also. One thing.
Thank you.
And second thing, you had presented the effect of Miham River basin. Okay, whether any similar type of study has been conducted in India in any of the river basin?
Thank you. Thank you, Dean Sridhar. I appreciate your comments. Thank you for your words of appreciation. Yes, I really enjoy talking about this topic, especially to our folks in Coimbatore. The main thing is the question that you are asking about the similar problems, whether or not we have in India. Of course, obviously, in many river basins in India, whether it is Kaveri or in the Ganges basin, we have these problems. But do we look at them in an integrated way? That is another question, looking at whether how one system, food system, is affecting water, or how water system is affecting the energy in an integrated way. I think there is some progress. There is some recognition of this issue by the stakeholders, including the state agencies and also at the central level. But I think it should be more. It should be given more, emphasis to really see how lower Kaveri, for example, are dealing with water problems, especially because of the development that's happening in the upper areas, or how the changes that's happening in the upper regions are impacting the lower Kaveri basin. That kind of connectedness needs to come. I mean, we are seeing that is being witnessed by the scientists, by the engineers, by the farmers, by the politicians or policymakers. But are we doing something about it? I think we are doing, but I think much more can be done. That's how I would say when it comes to South Indian river systems. But in the north, I would say in the Ganges, for example, the problems are manifold more. We have industrial pollution that's coming into the river. It's not just the water quantity problem. Now we are dealing with water quality problems also in those places. So I have not even talked about water quality problems, but Ganga Clean Action Plan is coming, or many other projects that are given to other institutions in India, for example, IIT Kanpur, IIT Bombay, IIT Delhi. They are doing substantial work in all of these areas. But again, I think, like I said before, with the power of data sets that we have, both from Indian satellites, from US, American and NASA-based products, are going to be really handy for understanding some of these, missing things that we have in the region. For example, how the Himalayas are behaving with respect to climate change. How is it going to feed the river systems in India, particularly the northern rivers? And then how is it going to really change over time by location? Upper Ganges versus lower Ganges, there is a huge difference. And all the way when it goes into the West Bengal region, how that is changing. And all kinds of problems that we have, the damming of rivers, pollution, and also because of extraction for agriculture, how all these things are combined is being done in bits and pieces, but I think much more can be done. That's what I wanted to say. That's where I want to leave it.
Thank you, Doctor, for your excellent presentation and excellent response also. And because of want of time, I request the participants to contact you through mail. If at all anything required by them, any clarification or additional information or something they want to get paper publishing something. Last year visit also you get given very good thought of publication. What is meant by publication? Without publication, no one will cite, especially in the scientific forum. So that also we could able to get it. So anything required from our forum, they will be contacting you through email. Okay, or just one aspect. Okay, thank you for your excellent presentation and excellent participation and timely occurrence of your slides in fitting manner. Thanks a lot. Thanks.
So thank you very much. I will certainly be glad to respond if anybody is contacting me by email for any questions related to the topic that I presented or for any of their research interest. Appreciate that. Thank you very much.
Thank you. Now, next, I'm happy to invite again our one more alumni, Dr. Audrey Anandi, Associate Professor, Biological Systems Engineering from Florida A&M University, US. So we are going to benefit because of your very good expected presentation on advanced engineering techniques in conservation of natural resources. So this topic is also a fitting topic, which is we have to get it benefited out of you. Madam, I am requesting you to make your presentation.
Good morning, everyone. For us, it's close to night 1 o'clock. It's 12:45 here. And can you all see the slide?
Yes, madam. Please proceed, madam. You can put your slides also.
Yeah. Can you see? I am sharing it.
Yeah. It's visible.
Okay. So I'm going to talk about advanced engineering techniques in conservation of natural resources. And I'm an associate professor. My name is Audrey Anandi, and I'm an associate professor in the Biological Systems Engineering program at Florida A&M University, Tallahassee, which is the capital of Florida. So I'd like to acknowledge Dean Sridhar and Dean Kennedy, as well as the organizing committee members for this opportunity. It's always, for me, I feel a lot of pressure and pleasure and honor to come back and talk to the students, and looking back so many years back, we were there in your place. And also I would like to acknowledge the different funding agencies that provided me with an opportunity to do some research work in some of these advanced technologies. So they are like USDA stands for United States Department of Agriculture, and NIFA is a part of that organization that has given several grants. The Department of Energy has given, and also National Science Foundation has given a grant. So this is a brief outline of my talk. I'm going to relate the topic to natural resource conservation engineering definition, and also how it is important and what are some of the opportunities that we can have in this field. Then the second part is I'm going to touch upon the different advanced techniques in terms of what are some of the advanced techniques for data collection, and how are we going to integrate the data, and also how are we going to look at analyzing the data after it is integrated. And finally, I'll finish it off with conclusion. So when I'm looking at the title, if you see the title, it has advanced techniques, advanced engineering techniques for natural resources. Here, if you're looking at natural resource conservation engineering, the definition of natural resource conservation engineering is the engineering analysis applied to natural resource systems that are encompassing MPEI. So that is management, protection, enhancement, and improvement of natural resources. So then what are natural resources? Natural resources are those substances that exist in the environment. So substances or energy that occurs in the environment naturally, and they are not created by humans. Soil, water, wildlife, forest, and air are some examples. And when we are looking at the definition, you can see that there are three highlighted components in the definition. The first one is the engineering analysis. And we are doing the engineering analysis to natural resource systems. So Dr. Sridhar was saying about systems thinking. So I'll also talk about systems thinking. So here we're looking at engineering analysis that is applied to natural resource systems. And when you're looking at that engineering analysis, it encompasses MPEI, Management, Protection, Enhancement, and Improvement of Natural Resources. Here you have to see we are using the terms natural resource systems and natural resources. And if you look at our own topic, you can see the title of today's topic is Advanced Engineering Techniques in Conservation of Natural Resources. So if you see the highlighted word, engineering techniques in conservation of natural resources can be related as natural resource conservation engineering also. So why is it important? As our population is increasing in the world, as Dr. Sridhar said, and we all are aware that the world population is increasing at an alarming rate, and the consumption of natural resources is also increasing. And because of overpopulation, human negligence, we are starting to overexploit some of the resources. If this continues, our future generations may not have any resources left for them. Hence, these resources should be conserved to maintain the ecological balance and save them for future generation. So proper management, protection, enhancement, and improvement prevents its destruction and exploitation, and we call that conservation. So when we conserve our natural resources, what we do is we support life by supporting the ecological balance. We ensure the future generations will be able to access the resources. We will preserve the biodiversity and make sure human race survives. So then take a few moments. Assume a world with no life and assume a world with no water, a world with no plants and a world with no natural resources. Then there would not be any life. So we saw that we have an increasing population, and based on Dr. Sridhar's slide, we also saw there is an increasing urban trend. People are moving towards the cities. But our natural resources are very limited. For example, water or land. But we need more food, we need more water and more energy. So by 2050, one of the scenarios, we need 70% more food, we need 80% more water and 55% more energy. But we have limited resources. That is where we as engineers play a very important role. So what are some opportunities? We have a lot of opportunities. We have opportunities as conservation scientists and engineers that are available throughout the world. There are some potential job titles could be natural resource conservation engineers, soil and water engineers, design engineers. It can be in federal agencies, central government agencies. It can be in the different state agencies, non-governmental agencies, private sector. And also we have some websites where we can look at some career paths on what is natural resource conservation systems engineer can look at. So these are just examples. In the next slide, I'm going to show you how I have gone around different state, federal, non-governmental organizations and private sectors before I've come into academics, all working on natural resource conservation engineering. So here, if you look at it, you can see I grew up in Chennai or Madras, and then I came to do my undergrad in agriculture engineering. I am Dr. Rajkumar's classmate. And while I was doing, after I did my agriculture engineering, some of the things that really stuck out for me is the project work and the different tours that we had in the curriculum. And that made me think and wanted me to do something that I wanted to do, make a difference in people's life. So I joined the agriculture engineering department, hydrology division in Kunur, as in a temporary position. And then I did not like working in a state government. So I wanted to do something. I went for my master's. I did my master's in civil engineering in Anna University in irrigation water management. There I did my project in ISRO in remote sensing data, using remote sensing data for water management. From there, I moved on to the software industry. That's when I got married and I moved to Bangalore. And then I worked in the software industry, which was design and development of softwares for different industries. I was not happy there too, so then I moved into a NGO and later into a state agency, Karnataka Remote Sensing Agency, where we were looking at remote sensing and GIS applications for coming out with action plans. From there, I did my PhD. I moved on to do my PhD in Indian Institute of Science in Civil Engineering. And I also did my first postdoc there before I moved to New York City Department of Environmental Protection. There I did my second postdoc, where it was in the geography department. It was a connection between the State Department and a university in the geography department. Later on in the agronomy department, I became a research assistant professor, and I'm currently an associate professor in the biological systems engineering program in Florida. So if you see, when I was showed in a previous slides opportunities across the world, all the time I have always been working on natural resource conservation engineering. But I had been in different parts. So first part of my career was in India. Now I'm in the US. You can see this. And the second part, if you see, all my education and my current position is in engineering. So the engineering training is helping me to identify what the problem is, how do I solve it? And then when I'm looking at the experience that I've worked in various other multidisciplines, you can see that experience is helping me to understand there is no clear problem or solution space, but there is a lot of fussiness and uncertainty in that space. So I'm going to now go to the second part of the talk, which is on advanced techniques. So here I have classified the advanced techniques into three categories: data collection, how we are going to integrate the data, and data analysis. Here I'm just going to give a brief outline of what these techniques are. And then I would leave it from there because a lot of the techniques were applied in Dr. Sridhar's talks. So when you're looking at the data collection, we can use remote sensing. Here, when we're saying remote sensing, it can be satellite remote sensing, it can be UAV vehicles, that is unmanned aerial vehicles, or sensors. So here, these technology can be used to collect data, and then we can integrate the data that can be used to provide information, advice to farmers as well as different policymakers and decision makers to help form informed decisions. So some examples of sensors that we have been using is, so you can look at location sensors. We can look at optical sensors. We can look at electrochemical sensors, mechanical sensors, dielectric soil sensors, and airflow sensors. These are just some examples I have mentioned here. So if you're looking at the function, what a location sensor tells us is, it's like the GPS of satellites. Like it gives us the location in terms of latitude, longitude, and altitude. The optical sensors use light to measure the properties of the soil. Many of you in your field experiments, you might have used one or more of these sensors. So these light sensors, when we measure the properties of the soil, they can be installed in the satellite, they can be installed in the drones or robots to determine the organic matter and moisture content of the soil. When you're looking at electrochemical sensors, here we try to come out with chemical data of the soils by detecting the ions in the soils, and also provides pH and soil nutrient levels. When you're looking at mechanical sensors, they are used to measure, for example, soil compaction or mechanical resistance. The dielectric soil moisture sensors can measure soil moisture by measuring the dielectric constant of the soil. Airflow sensors measure the air permeability. And when you're looking at the second part of the advanced techniques, where we are going to look at how are we going to integrate the data. We can use different types of thinking and conceptual models in addition to the physical models that Dr. Sridhar was talking about. So I'm going to talk about these thinking methods. In a traditional method, we think in straight lines. So we say A and B event. We have A, B, C, and D are events that are happening. So event A leads to C, B event also leads to C, and C event leads to D. That is, we think in an event-oriented thinking, or we think in straight lines. But when we are talking about systems thinking, which is a little more advanced technique, we think in loop. We say A leads to B, B leads to C, C leads to D, and D leads back to A. And this more complex one is the complex systems thinking. Similarly, you have another thinking loop where B leads to D, D leads to E, and E leads to C. You can see another, a loop. So these two loops come out with a big picture view of things. So if you look at my own career path, you see I had shown in an event-oriented thinking. One, it just goes in a straight line. But then if I am putting it in a systems thinking where the different components, food, water, energy, climate, and how the different techniques are coming, you can get more details about my career path. If you compare these two, you can see how a systems thinking can give you a better picture of the interconnections and the dependencies that are there. And here I've been talking about systems in the systems thinking. So it's important that I mention what systems thinking is. Systems is when I mean by this. So when I'm saying systems are a group of interrelated components, integrated to behave in a certain way and or serve certain purposes. They are normally under constraints and or external influences. For example, we have components 1, 2, 3, and these 4 circles are the different components. And within the components, they have relationships, attributes. And they are connected between together using relationships. So here we have components and they are interrelationships. So here the system and component can be interrelated terms. This is a system which has component. Each component can also be a system with smaller components. So this is how, if you look at Dr. Sridhar's, if you remember Dr. Sridhar's sign, he had given how the different components are related and how he emphasized the importance when you're making a decision or you're making an understanding of a system, it is important to see the interrelationships. And when we're talking about natural resources, here we need to be aware that natural resources are very complex. And then the complexity is there. So here it is complexity. When you're talking about complex systems, it's a state. Complexity is a state of having many parts, and it is very difficult to understand and find answers to. And complexity is present everywhere. It's omnipresent. When we live in an evidence age, we need to seek how do we address complexity. So in our program, what we do is we divide the complexity into three parts. The known knowns, the things that we know. The known unknowns, things we know that we don't know. And unknown unknowns, things that we know we don't know. So we have used this framework to address some of the complexity. And here when you're looking at complex systems, if you remember, this looks very similar to a systems systems thinking part. But here, instead of in a complex system, we'll have multiple large number of components. So that is what one of the major differences. The second difference is the system is more than the sum of the parts. So if we sum up all the parts, you get some information that is more than the sum. And here we have a collective behavior of a large group of components. In a systems, it need not have so many large components. Here we have in a complex systems, we have a large group of components and their relationships. And we have multiple, the relationships can be multiple nonlinear interconnections. That is very difficult to recognize, manage, and predict. So the next part is like Dr. Sridhar was talking about food, water, energy nexus. So what is this type of thinking? Nexus literally means connection between things in a series. And so here it is defined as one or more connections that is linking two or more things. So if you're looking at nexus, an infinite number of possible linkages and relationships happen. Again, here nexus thinking highlights relationships, interdependency, and the need for integrated decision making across multiple sectors or components. Here, some of them, nexus thinking, focus on system efficiency rather than productivity of isolated sectors. So when we are looking at models, here I'm going to talk about conceptual models. Dr. Sridhar said about, in his talk, gave a lot of mathematical models. So I'm going into the conceptual models. What are they? So conceptual model is an activity of deciding what to model and what not to model. So it's like a model abstraction. So a conceptual model is not software specific, but it is a description of a computer simulation model. It describes it, but it is not specific to a software. So it describes the objectives, what are the inputs, the outputs, the content, the assumptions, and simplifications of a model. And if you look at it, if you see there are physical models, scientific models, mathematical models, and abstract models. So conceptual model is part of all of them, but they are more abstract models. So why do we need conceptualizations and conceptual models? Why do you call this an advanced technique? Why do we need it? It's always an excellent first step to understand a system. It involves both mental or physical images and may not always be quantitative. It is used to collate and explain as well as solve the issues and problems relating to actual or predicted situations. It's considered as organizational diagrams that bring together and summarize information in a very logical and hierarchical way. It also helps with conceptual understanding. We can see the interconnections between concepts. It can be an important first step in developing a quantified models. So when we're going into the last part of the advanced techniques, data analysis, I'm going to talk about three concepts. One is artificial intelligence, machine learning, and deep learning. So here, now this is the best thing in US here. If you are looking for opportunities, this is a very good avenue for you to start your work there. So when you're looking at artificial intelligence, it's a very broad term. It aims to bring about intelligence behavior in machines. A subset of artificial intelligence is machine learning, where machine learning is to bring artificial intelligence through learning from the data. So my PhD work was on machine learning. And deep learning is a further subfield of machine learning. Here it extracts features from data, while handpicking features is simply not viable. So you can see the bigger component is artificial intelligence. Machine learning is a subfield of that, artificial intelligence, and deep learning is a subfield of machine learning. So in the next figure, you can see that interrelationship. So artificial intelligence can be any technique that enables computers to mimic human intelligence using logic, if-then rules, decision trees, and machine learning, including deep learning. So machine learning is a subset of AI that includes abstruse statistical techniques that enable machines to improve at tasks with experience. The category includes deep learning. And again, deep learning is a subset of machine learning. And it's composed of algorithms that permit software to train itself to perform tasks like speech image recognition by exposing multi-layered networks to large amounts of data. So when you're talking about complex data, we have a huge number of data, huge amount of data that we need to learn from. So that way we are looking at deep learning. So when we are looking at advanced technique, they are useful in understanding natural resource conservation engineering. And especially with the increasing stressors like population, urbanization, limited resources, and the need and demand for more food, water, and energy, these techniques are very useful. With this, I would like to conclude that the topic, part of my topic, engineering techniques in conservation of natural resources, is nothing but the definition of natural resource conservation engineering. And when we're talking about advanced engineering technique, it can be divided into data extraction, data collection. The techniques can be used for data, integrating data as well as analyzing data. So some of the techniques that we spoke about is systems thinking and how it is different from event-oriented thinking, complex systems thinking, nexus thinking, conceptualization and conceptual models. An example of conceptual model was the complexity framework that we spoke about, and artificial intelligence, other data mining or data analysis techniques like artificial intelligence, machine learning, and deep learning are some of the information and how we can get data from remote sensing. Here, the remote sensing could be satellite, UAV, or sensors. Whatever the technique, one thing you all have to remember is, whatever the technique or approach we choose, just be aware what we are missing. Are we looking at complex one? Are we missing the simplicity? If you are going in for a simple representation of a system, we have to be aware that we are missing out with the complexity. So whatever technique approach you choose, just be aware what you're missing. And also, as engineers, we have to work with multiple disciplines to look at the same problem in a different way, to come out with a very useful solution and to make maximum use of these advanced engineering techniques. With that, I am open to questions and discussion. So thank you.
Thank you, Dr. Anandi. Indeed, it's a very good presentation. You gave a complete experience, starting from school, BA degree, then Oliver, PG and PhD. It's a great actually motivation for all the students who are attending and for us also, because it's a great actually career. You can set so what you desire. So accordingly, you improve it. So thank you. And another important thing is that around 2 a.m. in the night, so you are still talking for us. So indeed, it gives a lot of attachment with the TNAU and of course our profession. So this is, it's remarkable. So just like that, it will not happen unless someone is associated with this and having the passion and attachment. So thank you indeed for this also. And overall the topic, you have given the complete exposure with what the latest techniques available. This is where we can use all these techniques, because so these are all like need of the hour. We need to collect the data and this artificial intelligence and so on. This area also we need to work and we have to come out, and overall I can say it is one of the best thing actually. So thank you, Anandi.
Thank you.
Thank you, Dr. Sridhar and Anandi. Our dean went to attend an important function, that is the launching of online UG admission form. So that's why we went in between. It is very informative, sir. Sridhar sir, it's very informative, and Anandi madam. So we have explained about the system, complex system, machine learning, deep learning, artificial intelligence, and we have related the how to find the solution in uncertainty circumstances, particularly with the example of your experience. That is very motivational. Really, it's a good. Students should listen or they should follow. It's a good path. So thank you very much. So that is Sridhar, sir. I want to some clarification regarding this. So your lecture, you have mentioned about the complete damming of the river system. So
yeah.
That definitely there will be a consequences in downstream side. Is there any study to optimize the minimum downstream flow to maintain the equilibrium like that? Or otherwise there will be a intrusion of seawater inside the system. So
Yes.
Is there any study available in your experience?
Yeah. Yeah, actually, that's a good question. Thanks, Professor Nagarajan. So thank you for your kind words. Yeah, I enjoyed Dr. Anandi's presentation too. Basically, the environmental flow requirement analysis that we do for the Mekong system is pretty broad. What we are understanding is if you allocate water for all the other purposes, there is not much water available for downstream. But if you introduce a constraint as how much water you should have minimum, downstream, and then impose those constraints right from the beginning in the water allocation for irrigation, hydropower, municipal industrial use, certainly we can make room, for making the remaining amount of water available for environmental flow conditions. In our case, we see about 10% number roughly is available for downstream side flow. This is primarily to keep the river alive and also to keep the fish aquatic habitats alive. And again, the temporary damming of this river for hydropower is not totally ruining the system downstream. But if you take the water for irrigation, that water is not available, right? So, that competing interest that we are having to deal with is quite alarming. And that's why I think there is always the conflict between environmental awareness, or people who are talking about green movements, or environmentally aware or friendly policies. They really don't think that all the other upstream abstractions will be a good thing. But as an engineer, when you look at it, people have a tendency to use every drop of the water. So we don't want to leave that water in the river. They think, oh, wow, it's going to the ocean. So why do we waste it? That's where that conflict, like Dr. Anandi was talking about, as engineers, we think in one way, but you have to see what the other side is thinking. And you want to really merge these two thoughts together. And we can be environmentally conscious, engineer who can really look at the both side of the puzzle and see how we can come to a solution. And that's what the system thinking is, and see how we can manage. Yes, the resource is limited. How do you divide that between different sectors, between different uses, is the common question that we have. But if you have better management strategy, I think there is always room to accommodate different needs or different demands. That's the lesson that I learned from the Mekong. And I think that's probably true for many other river basins. Environmental flow requirements, or EFR, or E-flows, they call, is really gaining a lot of interest and attention as we speak. Today, of course, I've completed this analysis and summarizing this as a manuscript. We looked at the Mekong system. We found out that how much you disturb the river. There are classes A, B, C through F. We ranked them, and different rivers, different segments have different types of issues. Some rivers are mildly modified, some are extremely modified. If you want to bring the river back to the original condition, how far you should go aggressively to bring from class F, which is the worst condition, to class A, which is slight moderation or change from the normal conditions. So from F to A, if you have to move the river in terms of classes, how much of an effort that you should have. For example, in many river basins in India, all of these are critically endangered, meaning many of these systems are already in the F category. And if you have to really change it to A or normal conditions, it's an uphill task. You have to really think about how to quantify the losses, how can we minimize the abstractions, how can we really optimize the use of water for multiple purposes, and then you will really slowly restore from F to E to D and back to original condition. That is for today's condition. And then we are actually throwing the climate change condition into the puzzle. So that actually even adds the complication. Different sectors, different locations within the system are stressed very differently. Spatial extent, I'm sorry, I did not include the slide, but certainly I'll be more than happy, Professor Nagarajan, if you would like to discuss that later. And if somebody is trying to do some research on this topic, I'll be more than happy to talk to the postgraduates or research scholars there. But it's an interesting topic. That's where I will stop. I don't know if I made sense, but
roughly we can take 10% flow as a optimal flow requirement for downstreams, right?
Yeah.
Is it,
yeah, 10.
Can we generalize? Is it applicable for all the basins?
No, No, that is possibly not the case. You know, for instance, in the Mekong system, I showed 10%, but in Idaho system, they told me very clearly what would be needed to maintain their fisheries downstream. So, which was a minimum of 300 CFS to 500 CFS. I'm sorry, I'm using British units here or English units. Cubic feet per second, 300 to 500, which is the normal amount of water that we see roughly during the dry season in Kaveri, for example, today. And that amount of water was needed for the farmers downstream to maintain fisheries. That was the requirement. So I know, like, what is the demand downstream side for this environmental flow requirement. So that I put in the whole complex, systems thinking. But it's again dependent on the river. Every river has a different environmental flow needs, and some rivers are pristine, some rivers are really undisturbed in a way, so we are okay. But many rivers in the downstream side are heavily manipulated, are heavily managed. So in those cases, how do you really optimize for environmental flow? Again, how much of a conscience that we have about keeping the river alive? That question comes back to deciding on how much allocation that you can have. 10% is the minimum number, but if you don't have any upstream structures, but most of it is going to be environmental flow, or half of it or more than that. So again, I think development of the basin can be done by taking into account environmental flow conditions. That way it will not have any conflict with any parties.
Thank you. Thank you.
Thank you, sir. You
Sure.
have given such a wonderful explanation. And one general question, actually, with respect to the Indian condition, where a general or forecast, because here they used to give the forecast, but it is not exactly matching in many situations. Is it due to we don't have much data or changing climatic condition? So, what will be the real reason, actually?
Yeah, excellent question, Professor Rajkumar. So I would say both, a combination of data and also, of course, the variability that we have in India from south to north, east to west is so diverse. Like here, so you need to have a model that really captures this natural variability. On top of the data that we deal with, these models rely on good ground truth, data from the field. Whether it is precipitation, temperature, or derived products like soil moisture, in our case, or evapotranspiration. We don't have them in many places in India. And here also it is true in the US. That's an opportunity, I would say, but it's also a heady task in terms of collecting the data. So it's a national effort, and also probably at the state level, at the watershed level, people can come up with some experimental approach to instrument the watershed, and then look at 5-year time, 10-year window, and see how the watershed characteristics are changing by time, and how that is informed with the data that is collected from the field in combination with a model. If we can really showcase that kind of an approach for one watershed, it could be Bhavani, it could be other watersheds in the area, that will actually convince other folks. I think there is no such experimental approach that we have in India. Maybe there are existing, but I'm not aware of it. But there are many experimental watersheds that we have in the US, and they are collecting data for not just for the recent times. We're talking about 50, 100 years. These are set up and collecting the data. That kind of approach will be needed. So coming back to the forecasting thing, we are looking at an empirical approach in India in most cases, but although now they are recently thinking about regional dynamical downscaling approaches from Pune and also from IMR or IMD in Delhi. They're moving along. The prediction is also challenging in Indian conditions, because we are talking about monsoons that starts in June, ends in November. And again, the rest of the months are really, dependent on what we have in those 4 months. I'm sorry to take some time here, but I want to, give some time for Anandi also to see if there is any other additional thoughts that she has. But, in Indian context, I think, there are efforts going on, but they are only limited in places. So we need to really understand how we can expand from Pune-based, forecasting approaches and IMD-based approaches in Delhi, with high-resolution products coming from different places. We have good data sources from satellite products and also from site-specific information from different locations, like Tamil Nadu Agriculture University producing extension-based, data sets from all these extension centers. Those can be aggregated. I think TNAU, for example, is ahead of the game than many other places, but I think that can be tapped into water-related projects. And forecasting is a key. Certainly, I agree with you. We need to have both, understanding of the physical processes from these global models. Weather research and forecasting, for example, that model is being currently used. They are modifying that significantly in Indian conditions, for Indian conditions, plus additional data that we have to collect from the field. They're right now using private companies produced forecasting data products. They are okay, but we need to really use them with caution.
Yeah, so I would like to add to it too. I would agree with what Dr. Sridhar said. In some places, we have very less data. In some places, but we have to make decisions with the available data. So that is where we have to use, we have to use simple models or models that are appropriate for that particular data set. But if you're using a very complex model and we don't have a data, what happens is we assume a lot of things or we abstract a lot of things which can come out with not a very representative result for that area. So it is important to be aware of what data we have and what type of models we have. There will always be a gap between, there can be a gap between what the model requires and what data we have. If they're both equal, then still model is an abstraction of the real world. It's a simplified mathematical representation of the real world. So we have to be aware that it is very difficult to represent the complexity of the real world situation because, as Dr. Sridhar said, it's multiple disciplines are involved. There are multiple views of the same problem, whether you're looking at an environmental point of view, an engineering solution, or a conservation biodiversity solution. So if you're looking at a river basin system, you have animals, plants, we have humans, and then we have engineering infrastructure. So how are we going to, balance all of that, and how are we going to model that? That part of it is very important from how much data we have.
Okay, thank you so much. Both of you explained very nicely and sparing your valuable time, again, it cannot be matched. So thank you again. And I would like to inform you that next month we are going to organize the World Food Day on October 12th. So we will invite you for a short talk, in fact, and you need to give. So it's a request, and also we will invite. It will be organized on October 12th. Normally it falls on October 16th. So here it's so much of holidays. So we are just preparing it on October 12th. So this is for the kind information and also invitation. So thank you very much for spending your valuable time and giving such a wonderful and excellent. Okay, in this aspect, both of you really, you gave. It's like eye opener. Okay, all the aspect how to conserve water, what are the models, so many things you did. So thank you so much. Thank you.
Sure. Thank you.
Thank you. Bye.
I'll take leave of you now.
Yeah.
Bye-bye.
Thank you.
Yeah.
Bye.
Bye-bye. Yeah.
Good morning, everyone present here. So myself, Nisha. I am working as a teaching assistant in the Department of Foundational and Power. So today I am going to present on the topic development of tractor finger millet. So finger millet, which is also known as ragi, is valued as a staple food crop in India. It is called as the fourth cereal. So the height of the ragi is 170 centimeter, which can be used both for fodder and grain. So this development of this tractor frame-mounted finger millet harvester helps to harvest the finger millet crop so that we can use it as a fodder and also a grain. The importance of finger millet cultivation. So finger millets can be grown even in poor soil and also in adverse climatic conditions such as low rainfall and intensity. So this finger millet crop provides both nutritious grain and fodder. The grain obtained from a hectare of land is 20 to 25 quintal, and the fodder obtained is 60 to 80 quintal per hectare. So it will be a valuable source both for fodder and grain. So this it is a valuable source of forage because it has a rapid growth and a high nutritive value.
Presentation, I can remove your speech.
The finger millets, they are harvested when the ear has turned brown and it does not possess uniform maturity. The finger millet crop does not possess uniform maturity. While harvesting, the green ones are also harvested and it will be undergone curing by keeping the finger millets for 1 to 2 days in shade. The manual harvesting of finger millet is done using sickle. So nowadays, both the rain-fed and the irrigated farmers are harvesting the finger millet using sickle. When using sickle, we can harvest the earheads and the stalks separately, and we can use it as a fodder and also the grain. The main issue in manual harvesting is the labor charges and the scarcity of labor because it needs 25 woman days per hectare for harvesting the area. Which in turn increases the cost of production. And then coming to mechanical harvesting, the farmers are using both self-propelled reaper and the tractor front-mounted reaper. In that case, the whole crop is harvested and we can't harvest the earheads and the stalks separately. So again, it requires labor for separating the earheads from the stalk. So the requirement is the tractor front-mounted harvester which will combine both the operation. That is, which will harvest the earheads and also which will harvest the stalks alone. Single pass. So this is the concept of the tractor front-mounted finger millet harvester. So the concept of vertical conveyor reaper is utilized in my design. So in my design, I have included two cutter bars. One is to cut the first cut, that is the bottom cut above the ground level, 10 centimeter above the ground level, and the next cut is at 46 centimeter above the ground level, which is the mean height of the or the average height of the earheads. So this is the finger millet tractor front-mounted finger millet harvester. So the components are, it consists of two cutting units. One is the lower cutting unit and another one is the upper cutting unit. So the upper cutting unit is 200 mm in a horizontal offset to that of the lower cutting unit. And it also consists of a conveying system for conveying the harvester earheads and collecting it in the collection bin on the left of the harvester. And also at the bottom there will be a conveying system and a flat bed conveyor for conveying the harvested stalk and windrowing it in the field. So these are the components. So the harvesting unit includes the upper cutting unit and the lower cutting unit. So power for the cutting unit is obtained from the tractor PTO. And next is the reel. Reel is used for pulling the crops so that it can be harvested from by the upper cutting unit. And next is the collection and conveying system. For the conveying system for the ear heads, I have used a screw conveyor which will convey the harvested crops to the left of the unit, and hence it can be collected in the ear collection bin. And next is the conveying system for stalls, which includes a gathering mechanism and consists of a crop divider and a star wheel and a flatbed conveyor so that the stalls can be windrowed in the field. And next is the supporting wheel, which is used as a support and for balancing while traveling in the road. So this is the developed tractor front-mounted finger-millet harvester. So this is the schematic diagram of power transmission. So the power was taken from the tractor PTO, and using the belt pulley it is transferred down it is attached, the shaft is attached to the lower portion of the tractor, and using telescopic shaft the power is given to the total equipment or the unit. So first I have used a bevel gear so that it will give power to the lower cutting unit, and by using a flatbed conveyor the power is given to the upper cutting unit and also to the screw conveyor and the reel mechanism. These are the selected variables. So the variables selected were reel rotational speed, reel mounting height, and forward speed. So reel rotational speed, it has greater impact on the harvesting efficiency. And based on the previous research, I have selected the reel rotational speed as 30, 35, and 40 RPM. And also the reel mounting height, the effect of reel mounting height will be more when going on to the harvesting efficiency and also on the losses. I have derived from the calculation that the reel mounting height will be, the optimized reel mounting height can be 40 centimeter. So I kept a lower value and a higher value, and then selected the variable as 35, 40, and 45 centimeter. And the forward speed is tractor first, second, and third gear, lower gear 1.6, 2.68, and 3.48 kilometer per hour. The response variable is harvesting efficiency. Harvesting efficiency is calculated using this formula. So total number of crops that is on the field is calculated for 2.5 meter square area, and the total number of crops that is uncut after harvesting is also measured, and by this expression we can calculate the harvesting efficiency. Coming to the effect of reel rotational speed at selected levels of reel mounting height and forward speed. So it is noticed that the high efficiency of 89% was found at 30 RPM reel rotational speed and 40 centimeter reel mounting height. So the percentage reduction was when comparing 30 RPM and 35 RPM, there was 1.4% reduction in harvesting efficiency, and when comparing 30 and 40 RPM, there were 3.84% reduction in harvesting efficiency. So this is due to the fact that when the reel rotational speed is increased, the reel failed to push the crop towards the upper cutting unit, so the cutting was not efficient. Hence, there was reduction in the harvesting efficiency when the reel rotational speed was increased. Next is the effect of reel mounting height at selected levels of reel rotational speed and forward speed. So when comparing 40 centimeter and 35 centimeter reel mounting height, there was a reduction of 4.6% harvesting efficiency, and when comparing 40 and 45 centimeter, there was a reduction of 6.7% harvesting efficiency. So this is due to the fact that when the clearance is increased, when the reel mounting height is either increased or decreased, the clearance between the reel and the upper cutting unit is increased. So hence it causes failure in holding the large crop. So there will be many large crop. So the upper cutting unit failed to hold the large crop for cutting. And the next is the effect of forward speed at selected levels of reel rotational speed and reel mounting height on harvesting efficiency. So the maximum efficiency of 91.5% harvesting efficiency was noted at 1.6 km per hour forward speed and 30 RPM reel rotational speed. And when comparing 1.6 and 2.68 forward speed, there was a reduction of 1.5% in harvesting efficiency. And when comparing 1.6 and 3.48 forward speed, there was a reduction of 9.1%. So this is due to the fact that when the forward speed is increased, the crop slipped from the both the reel and also from the upper cutting unit. So the harvesting efficiency was low at increased forward speeds. So I'll conclude that the maximum harvesting efficiency noted was 91.5%, and all the reel rotational speed, reel mounting height, and forward speed, the three variables, they show noted effect on the harvesting efficiency, and the optimized values obtained were 30 rpm reel rotational speed, 40 centimeter reel mounting height, and 1.6 kilometer per hour forward speed. So these are the harvested ear heads by the upper cutting unit, and this was the height of stubble that is left in the field after harvesting. And this is the windrow stack in the field, and that is the field view after harvesting. Yes. Yes. Yes, sir.
The speed of ATU?
So 5
The wheel speed, as you told, is around 35 or something, but the speed you can see that it is more than that, not 35.
This is not the field evaluation, so this is for study. So I think this is 45 rpm, while the video is taken, it is 45 rpm.
How to measure the RPM of reel?
Using tachymeter in the shaft.
When you get to load out, this.
Yes, so hydraulic cylinders were provided to lift and lower, for lifting and lowering of the units.
Speed you have mentioned that is it like independent variable? Speed, not the
Forward.
yeah.
Yes.
Independent, how you measure it? It's like 1.6, 2.68. It's possible to fix like that?
No. It is the speed that is given from the manufacturer. For the first flow and second flow and third flow.
Cannot be your independent
No,
variable.
sir, it is not made. It is the speed given from the manufacturer.
Most respected Dean Engineering AGSC and most respected Professor and Head Soil Water Conservation Engineering, and most respected Professor and Head Process Engineering, and then lead speakers, and then friends. Good morning to all. Today we are going to discuss about the factors affecting the performance of a mechanical linkage picking fingers during automatic transplanting of vegetable variables. So in this, there are mainly two factors which is mainly influencing the design and development of the automatic vegetable seedling transplanting mechanism. So the one is a horticultural factor and another one is a mechanical factor. So in this horizontal factor, it includes age of the seedlings, media, moisture content, and what type of the media which we are going to be used for during the transplanting. So and then progress cell size, which are all comes under the horticultural factor. When we are talking about the mechanical factor, so there are many of them. So the core factor is the designing of the picking finger. So that one is the main impact of the designing of the transplanting mechanism. And then another one important factor is the needed angle. So at what angle which we are approaching is the processor. So these are the main two factors which is going to affect in the design and development of the automatic transplanting mechanism. Actually, the first top three pictures which is indicates the conventional method of vegetable transplanting in the main field. Initially, the farmers are randomly shown in the main field itself, and then later on it will be transplanted into the main field. So after some certain period, it will take, if it is a tomato, it will take 23 to 30 days. So during this process, the seedlings may get severe injury during the manual transplanting of this process. And also the root establishment is also very, it will take many more time of the root establishment. So for that, the farmers are nowadays moved to the prograde techniques. So the prograde is one, is used to raise seedlings in a good manner. So nowadays there are many progrades are available in the market. So here for the study I have taken three types of prograde, which are all commercially available in the market and which is used by the farmers also. So based upon this research, I have taken the three types of progrades here. So after raising the seedlings with the help of the prograde, and then later it will be transplanted with the main field. So when we enter into the automatic transplanting mechanism, so why initially it is needed for the automatic transplanting mechanism? So there are two factors. One is the transplanting of seedlings to the main field. It is a very labor shortage one, and also it is a tedious operation for the farmers. Okay, so at the time of doing the transplanting, the farmers are getting the bending posture at the time of transplanting. So it will lead to very tedious operation for the farmers. And another one more factor is that even though nowadays there are many type of semi-automatic transplanting or developed. So in the semi-automatic transplanting, so the seedlings are fed by manually and metered by mechanically. Okay. So in that, during the feeding of seedlings by the manual, so operator may exhaust the energy. It should be in the condition. In the case of if you take the automatic transplanting, the seedlings are fed by mechanically and then metered by it is also by mechanical. So by this, so it will be relatively high speed during the operation, and it is also we can save the labors. And actually, this is my conceptual design of transplanting mechanism. So here I designed based upon the optimization of the previous studies. Actually, this is one part of the study. So here I have taken the 90 cell probe for a particular study. So the conceptual design will be incorporated here. Actually, the first step of the design is we should approach the seedlings with the help of the designed finger. And then second step is the piercing the seedlings within the protracer. And third step is the grasping the seedlings with the help of the mechanical linkage. And then extract the seedlings from the protracer. And then it will be moved to the particular desired position. And then final stage is the releasing of the seedlings. So these are all the operations which we carried out during the transplanting operation. Actually, these are all the developed experimental setup for optimize the selected variables. Here I have selected the three variables. One is the media moisture, based upon I have said in the first slide itself that factors will be the horticulture factor and the mechanical factor. In the horticulture factor, the media moisture content. Here I have taken the three types of media moisture content, and then in the case of mechanical finger, I have designed and developed three different types of mechanical linkage switching finger, and then three types of needle angle. So with this, I have designed and developed one experimental setup for optimizing the variables. Actually, the experimental setup is consisting of a main frame, which is used to assemble the all other units, and then conveyor, which is used to convey the seedlings to the mechanical finger, and then linear gateway, which is used to transferring the seedlings in the linear manner, and it will be transfer the seedlings from the protrator into the desired position. And then here I have used two pneumatic cylinders, one for grasping the seedlings and another for extract the seedlings from the protracer. And all other operations are controlled by the PLC. So that is not PLC is nothing but programmable logical control. So the entire operation is controlled with the help of the program, which is already installed in the PLC board. So after optimized the particular variable, so here I have designed another one more development experimental. Here, so this is the one to pick the first row of rotary seedlings simultaneously. So the previous one is only one seedlings picked by the mechanical finger. So after optimizing the variable, I have developed this experimental setup to pick and transplant the entire first row of the rotary seedlings during the transplanting operation. So it will show the, and also it will need reducing the time of transplanting also. So it is also consisting of a number of components. Here I have used three sets of pneumatic cylinders. So which are one for the piercing and grasping the seedlings from the protracer, and another two, both the end we have used another set of pneumatic cylinder which is used to transfer the seedlings from the protracer to the conveyor, slotted conveyor, and then another one for top we have used another set of pneumatic cylinder which is used to extract the seedlings from the protracer cells. And another one more conveyor which I have added in this design. So that is for slotted conveyor which is used to transferring the seedlings in the desired position during the transplanting operation. So actually, this is a step-by-step process of the operation. First, approach the seedlings with the optimized finger. So with the help of the top set of the pneumatic cylinder. So with the help of the top set of pneumatic cylinder, initially it will enter into this cylinder protracer cell. So with the help of the 7 numbers of picking cylinder, So it will grasp the seedlings with the help of the design developed mechanical finger, and then fourth step is extract the seedlings or remove the seedlings from the protray cell with the help of the top two cylinders, set of the cylinder, pneumatic cylinder, and then with the help of the both the end big cylinder, it can be transferred to the slotted conveyor. So here I have used the PLC hardware for entire operation. So the left side indicates the PLC hardware. So PLC is nothing but programmable logical control. So that is entire. Yes. So on the right side indicates the logical operation of the transplanting operation. So actually, it shows the effects of the selected variables on the picking efficiency of the transplanting. So during the at 8-degree needle angle, it shows the maximum picking efficiency. So and so if you see about the another two angles, so it will relatively very less picking efficiency because if the angle will be converged, so it will lead to damage the seedlings. So and also it will if the angle will be more, it will be damage the protray and also medium also, and also it will be more influencing in this training. So when it is concluded, so with the help of the developed transplanting mechanism, the transplanting rate will be 2,520 seedlings per hour. So I have chosen the three types of double seedlings, the tomato chili brinjal. So the success picking rate will be 89, 95 and 91 respectively. So the missing seedlings are actually as compared to this, among these three seedlings, tomato is quite little compared to the other two seedlings. So that's why the picking efficiency is also very less. So here I would like to show some of the video clipping on the development mechanism. Actually, ongoing video for only first row.
Lab condition.
As we
have tried
actually,
analysis. Success rate, each mechanism success rate.
sliding end can type, sliding end can type do the no. Actually, we are talking over mechanism, which is 85, 82 to 85 percentage of every campus will give 80%, nearly 90%. In case of tomato students.
So if the STEM is relatively hard,
Yeah.
success rate is
Yes, that's also more influencing factor.
no, that means you are talking about 10% is damaged or not at all picking.
It will be the sum of the damage and the failure and the non-secondary all other related elements.
Mechanism, as you told, it is going on, it is not over actually.
Yeah, sir, actually the part of the transplant. The thing is,
Other example, already something being developed in our area, seeing that it's total, the mechanism is developed. It is what you know.
here also, so that is pushback number, sir. So that's also very
Problems actually persist.
Okay. So good.
thanks.
Yeah, it's,
Moving to another presenter, my research topic is on laboratory study on effect of temperature and particle size on CN visa oil production. with respect to moisture, it accounts for about up to 10%, sir. Then up to 70 to 80% upon the biomass, sir. For parent stuff is very low, only 56 to 60%. For PGMP and non-crop, it will be very high, 70 to 80%. And then dash accounts for about 15 to 5 to 50%. It depends, it varies on the feedstock we have selected.
Okay.
Good morning to one and all present here. Today I'm going to present on LULC change deduction in Lower Bhavani Basin. The main aim of the study was to estimate the efficiency of Google Earth Engine in the estimation of land use land cover. So first, getting into the introduction. First, let me tell you what is the difference between a land cover and land use. Land cover is nothing but it refers to the physical and biological cover over the surface of the land. It may be either vegetation or a water body or artificial structures. Land use is nothing but how humans use the biological or ecological properties of the land, how it is put into use. So basically, when remote sensing data has been used for classification over the years because of the temporal resolution as well as repetitive capacities of remote sensing data. So what happens is that as the satellites have increased and the resolutions of images have also been increasing. So due to this fact that the computational time is also increasing and the cost of computation is increasing due to the system efficiency time and everything is getting increased. So what we can go in for further analysis is that we can go into Google Earth Engine, whereas this is a multi-petadata based efficient tool for analysis. So this has both, sorry, I didn't explain this. So here the first GIF shows the that is happening over the years. And the second GIF here shows the deforestation occurs over the years. So this is just a time-lapse video, just to identify how an satellite image is used for temporal studies over the time and space. So this can be used for ecological landscape at regional level, a long-term temporal perspective, and to assess the main and past trends of the drivers of landscape change. So this Google Earth Engine is a freely available tool that anybody can use it. The only requirement is that you have to just create a registration link and they have to approve your login and user credentials. And you can start using the Google Earth Engine. So this, what is the merit about Google Earth Engine is that it has both a graphical user interface and as well an application code editor. So whereas in graphical user interface, you can zoom in your images what you need and the area of interest, region of interest can be viewed in that viewing the composite images. And an API code editor, a user can interface his code. He can give a JavaScript or a Python code and execute his output. So for this study, I've taken Lower Bhavani Basin as my study area. So this was generated using AGSC. So this mainly comprises, it comes under the district of Erode and parts of Tirupur and Coimbatore. Now I'll explain the methodologies that was taken. So first is the Google Earth Engine. I will just display the interface of it. So this is the main interface of the Google Earth Engine. You have a code editor there and a map observing session at the bottom. So you can zoom into your region of interest, or in either way you can give your code to zoom into the region of interest by selecting further options like region of interest, the date, what you want images to occur, and specifying your cloud percentage in which you want to appear. Generally, cloud percent is kept as below 5% for better efficiency of results. And this is a console on the right-hand side, wherein you can export your outputs to a ArcGIS platform or as an image platform, With that, you can do the further computations. So this is your asset manager. You can give your shape files or your boundary layers or your tables. Or user can input their layers using the asset manager table. So and code they can give you a code and run it, and the script will run the code, and all the outputs will be in the console section. From that, they can derive the outputs. For my study, I considered Google Earth Engine as an archive of data sets. It has from Landsat to Sentinel. Landsat is a 30-meter resolution data, and it has a temporal resolution of 16 days. So this top of atmosphere collection was used for the study due to the landscape because I assessed the landscape changes. So this was my region of interest, and this was a path and row image for my region of interest. And this was generated using the code, and this is a composite image for the date 2014 and 2019. The separate codes were run for 2014 and 2019. And next, after obtaining my image, the filtering options were performed using a code, wherein the region of interest, this is the Lower Bhavani Basin as I showed earlier, the code was generated and it was developed. So this here shows the imagery with the 2% cloud cover and the date range of 2014, and that is for 2019. This was giving the training data sessions. So we have to train there are built-in algorithms in Google Earth Engine. So when we train it, and as the speaker mentioned, they have machine learning algorithms inside, and that will classify and give your output results to better accuracy. Training data sets, the major 5 classes were assumed in the study. One is the water body, agricultural land, fallow land, and built-up area. These are the 5 major classes that was assessed in the study. So here in this image, the blue color indicates the water bodies. I'll just show it in the next image, the classified image. This is where the training points, total of 220 training points were used for the classification of the classifiers. And this is a high resolution imagery that was used for classification. So it is very visible, the water body is very visible here. And then these are the built-up areas, and these are the agricultural lands and the fallow lands. So by using this technique, all the points trained data is nothing but a feature collection. It contains class numbers starting from 0, 1, 2, and 3. And you can give in your region, you can give in your classes, either it's a water body or a build-up. And based on that, it will take its classification. This RF random forest was used for the classification. So this is nothing but it creates multiple cartilage trees. So this mainly prevents an overestimation of the data. So next, going to the accuracy assessment, I used a conclusion matrix to find out the accuracy of the study. So by only 30% of the training data set was used for the accuracy assessment, and it was found that it was 85% accurate, the analysis. So finally, the land use land cover map was generated. And this is clearly evidence that the vegetation is agricultural areas indicated in light green color, and the top portion indicates the forest area, and the yellow color indicates the fallow lands, and the blue area indicates the water body, and the white area indicates the built-up. So it is very evident from the map from 2014, and that is 2019. So wherein we go in for the accuracy distribution in comparison for the 2 years, I've just compared it for the 2 years. So the major classes were agriculture, built-up, current fallow, forest, and water body. So in comparison with agriculture in 2014 and 2019, it was found to be a little higher than in 2014. And next, the build-up was also increased due to urban sprawl. And the current fallow lands were decreased because the fallow lands were put into agricultural use. And the forest, there was no much change in the forest area. And water body also, there was no much change in the 5 years period of transition time. So moving into the in detail change reduction analysis. From 2014 to 19, the major classes forest to forest, or either current fallow to fallow, or agriculture to agriculture, these were the percentage that remained the same in both the years. And major change was observed in current fallow to agricultural land, as I said earlier, from 2019. So there was a 7% increase in 2019. And from agricultural area was converted to build up to 2%. That was a minor change there. So to conclude, From all these studies, like it is very evident that Google Earth Engine can be used as an effective tool to find out the either landscape change, or this can be used in for further studies as for policy or decision makers to arrive in for their detailed reports. And this main adaptability is that it is a petabyte-based, cloud-based performance. So a user need not download a data to a system or process it, and it mainly reduces the storage capacity and computational time. So the user can efficiently, and it's very less time-consuming process, and the outputs can be obtained at a very accurate and very fast compatible time. Thank you.
So, when we compare to years, different years, well, there is no change in water resources. But it's observed that increase in agriculture area.
Yes.
That means the water use efficiency has increased, or
Actually, the area this in such just identifies the difference in the area, sir. Yes, sir. What this depicts is that from 2014, fallow lands they have been put into agricultural use, so there is a reduction.
But the change means irrigation, or
Sir,
it
that
includes
both, sir, because we didn't go into any detailed study, sir. So this is a basic study from which any user can further use the study. So this can be used effectively for their.
assess the accuracy of the study.
Sir, confusion matrix was used, sir.
Confusion matrix.
Yes, sir. That was built in the code built in Google Earth Engine, sir. What we do is that we have given training data sets, sir, up to 20 points. From that, 30% of the training data to.
Training, is it related to fuzzy or?
So no, sir, like the random forest classification, sir. The training data in the sense like we are training the classifier that this is a water body, this is the land use part, this is the built-up area. So this is the, yes, sir. We have to initially train the classifier. So if we give around 220 points, that will generate around 1,000 to 2,000 points, and that will accurately measure that this is a water body. Based on it, the decision trees that will decide that this is a water body and this is a land use.
It's good that so we can use only the data.
Yes.
That is even instead of even 2015, you can go for.
Yeah, you can go in for temporal studies ranging from 1999. That is based on the computation of the Landsat imagery, sir. If you go in for earlier sets of data, you just have to process the data and then use it. If you go in for latest versions of Landsat, Sentinel or MODIS, you can directly get the data from the archives and you can process the data, sir.
So these, the previous 99, those data are already available.
Yes, sir, it is available, but we have to do certain processing, sir. That will not be radiometrically corrected.
Okay.
So we have to just radiometrically correct it and do some processing, cloud maskings as well, and then we can use the data.
So we can, instead of the GIS and all, so what we used like remote sensing.
Yes, sir.
Okay.
That was recently used, but the recent trend is that going for a storage, cloud-based storage will be better than storing it in your system.
Yeah. So that we can use.
Yes.
Instead of taking huge data,
Yes.
analyzing, we can use this Google data.
This has a cloud server as well. So user need not download anything or process anything in the system. It will be all processed cloud-based, just in a click of a button. If you just give your code and you give it a run, all the processing will be done cloud-based. So your computational time will also be reduced.
Or recently, is there any some devastation?
Yes.
Due to cyclone or something, how it can be exactly monitored by using this system?
So like if you want for way back data to now to find out the climate forms or to find out whether the rainfall pattern has changed, they have various indices for that, sir. For vegetation, if you want to know for the over the years, there's NDVI indices and you have SPI indices. So using that indices, we have to develop a code. So using the water index and the NWDI index, we can develop the code and from that we can find out so that year to this year what has been the change and what was impacting the change. When we go into further analysis, we can find out that using those various indices.
Good.
Thank you. Thank you. Thank you.
Afternoon, Anand present here. Today it's time for you to present a topic on Markov chain model of weekly rainfall probability and dry and wet spell agricultural planning and in Dharmapuri districts of Tamil Nadu. So before getting into the topic, I would first want to clear you the major doubt whenever we go into the topic of dryland agriculture, like dryland farming agriculture or rain-fed agriculture. So first of all, what is dry farming? The dry farming is like the dryland agriculture is basically classified into three major agriculture forms, that is dryland farming, dry farming and rain-fed farming. In dry farming, the area receives less than 750 mm of rainfall. In a dryland agriculture, the dryland agriculture, the rainfall receives of 750 to 1150 mm. In rain-fed agriculture, the maximum we consider as 1150 mm of rainfall. So here, the study area which I have chosen, that is Dharmapuri districts, mainly comes under the rain-fed agriculture condition.
It's not dry.
No, sir. So, and before going further, I would like to show some of the data published from the Ministry of Agriculture in the 2011 census, like how much in the Indian condition, like how much area comes under rain-fed land. So, if we take that census, there around 44% of area of production comes from the rain-fed land. And if you see the net zone area, it has like around 140 million hectares. And if you see the irrigated land, it is around 65.3 million hectares. And here we will arise many doubts like how that the net zone area is this much, but we get a rain-fed production only 40%. The major reason is like in the rain-fed agriculture or dryland agriculture, we mainly dependent on the rainfall. So if we depend, like as we all know, rainfall is a probabilistic event. It is not a, we cannot say like 200 mm will occur in next day. It is always comes under probability. So in Indian, many ministries like agriculture ministry, food ministries are taking many steps in increasing the livelihoods of farmers, like bringing in many schemes like irrigation funds. Then recently, one Abhiyan has started like catch the rain campaign. That is with the theme of catch the rain where it falls, when it falls. Like by adopting many technologies of like as a soil and water conservationist, I can list many conservation practices like bund farming, starting based on a slope and soil conditions. I can list n number of practices. So by proceeding my presentation with that note, I wanted to give a short introduction of the model which I have taken for the study. That is, as we all know, Indian agriculture is mainly dependent on monsoon rainfall and its distribution over the area. And the yield of crops, particularly in rain-fed condition, depends mainly on the rainfall pattern. And hence, many researchers have tried their best to bring the present the research findings and the behavior of rainfall. And in my study, I have mainly taken up wet and dry spell analysis to characterization of command area crop scrapping pattern, planning and design of conservation structures. So the major methodology which I have used, as I mentioned in a topic, that is Markovian chain analysis, it is a probabilistic model. So for such kind of models, we cannot go for a short years of data. We have to go more than 30 years of data. That is like normal years data we call. So here I have used around 40 years of rainfall data, which I collected from Regional Meteorological Center, Chennai, Tamil Nadu. So here I have used this data for analyzing dry and wet spell analysis to carry out the weekly analysis of the Markovian chain process. So here in Markovian chain, we use the standard week data. So the entire year we divided into 52 standard weeks. So based on that data, like in 1 week, the total sum of rainfall like around 20 mm. Here for this area is considered by the Ray et al. In 2018, considered as a 20 mm rainfall in a week is considered as a dry week. Less than that, if it is more than that, we consider as a wet week. And mainly the dry spells strongly occurs due to the inadequate rainfall throughout the year, throughout the mainly rainy seasons. So the study area which I am mainly concentrating on is Dharmapuri district, which was created in 1965. Before that, it was coming under Salem district, and this area is mainly distributed in a 11 degree 47 minutes and 12 degree 33 north latitude, and 77 degree 45 degree minute and 76 degree 45 minute east longitude. So here the average annual rainfall is 1150 mm. That's why it comes under rain-fed condition, with the temperature ranging from 17 degrees centigrade to 37 degrees centigrade. And here the major crops which they concentrate are paddy, ragi, legumes, groundnut, sugarcane, cotton, coconut, and farm. Because it comes under rain-fed area, mainly the less water requirement, and in some areas they will go for a high water requirement with the supplemental irrigation practices. So how this model works, that we'll see. So here, this model mainly helps in spell distribution analysis, and the model assumes that the probability of rainfall occurring on any day depends on whether the previous day was wet or dry. Like tomorrow is I'm going to calculate for tomorrow. The model takes today's result, whether this day is wet or dry. So the model calculates the initial probabilities of getting dry spell or wet spell in given standard meteorological week. So the calculation of conditional probability provides the information of whether the dry spell followed by dry spell or it follows wet spell. The same way for the other spells. And the rainfall probability analysis useful in adjusting crop sowing dates in such a way that critical stages of crop production coincide with the period of higher rainfall probability. Why we go for this? Like mainly for the farmers at the end user. Whatever the research we carry, we should have a human element involved in this. So here, mainly for Markovian analysis, mainly useful to the farmers under the rainfall conditions. That's why here the sowing date, they have to plan such a way that critical period of the crop should not come in under the lowest rainfall probability condition. So the farmer has to go in such a way. So here mainly the three probabilities we will consider: initial probability, conditional probability, yes, consecutive dry and wet probability,
And initially, the initial probability will be taken as number of dry periods divided by number of dry weeks divided by total number of years. The same way for a wet week. And for consecutive, the number of consecutive dry weeks divided by the number of initial wet weeks, dry weeks. And the same way for the number of consecutive dry, like PDD, 3 consecutive weeks, will be taken as initial week, then second consecutive dry weeks, and third consecutive dry weeks, 3 consecutive dry weeks. So the same way will apply for the wet weeks also. So another method I used is forward and backward accumulation. Here I just go in the short note. Here, like complete years, what we take divided into 52 standard week, we take from the monsoon started week. We just go with the forward accumulation method, like adding the every week rainfall. So when it comes to 75 or 75 mm. And 200 mm, we will mark that particular week. The same way we will come with the backward way. That is from the starting 52 week, where it reaches 300 mm or 400 mm. That we take as a that we consider for the planning for conservation structures, sowing of crop. So this is the weekly wise rainfall distribution of the Dharmapuri districts over the 40 years of data. And here I just wanted to deliver like how this wet condition of that particular area is as distributed over the standard weeks. So if you see, we can see from 33 from the week 33, like the monsoon started and it ends by the week of 45th week. And based on this, the crop planning strategies has taken place. The dry probabilities are during the Kharif, like 23rd week to 32nd week of standard weeks. So here the groundnut, pigeon pea, pearl millet, maize, sorghum, green gram, soya bean, sunflower, which requires very less amount of water, will be sowed. And the successive dry weeks in the middle rainfall weeks need supplemental irrigation when we take up such cropping. So in 37 to 44th week, there will be high rainfall week. So there we take up the rabi crops, and here cotton, rice, vegetables, such kind of crops we can go for. And under this, based on the proper land leveling grading, we can increase the water use efficiency. By increasing water use efficiency, we can increase the water storage capacity, increase the soil moisture bearing capacity also. So major findings from this study are frequent occurrence of early, intermittent and late season continuous dry spells occurs in Dharmapuri district. Here, Kharif crop requires supplemental irrigation, and short duration crops and less water crops are mainly suggested in this area. And wet weeks is around 22% during the 16th to 18th weeks. So in this particular time, we can plan for a high water requirement crop, and summer plowing will be planned in the initial days of the year. And mean duration of rainy season observed as 14 weeks in this particular region. Thank you one and all for the patient listening. Thank you.
So defining dry farming, dry land agriculture, rainfed agriculture, you have mentioned some ways.
Yes. Dry farming is less than 750 acres. Dry land.
So what is the annual average rainfall of Dharmapuri district?
So 1,150.
When we say it's dry district?
So rain-fed.
It's a rainfed district. That's just a dry like Ramnad.
Okay, but is it sufficient to mention only the total amount of rainfall? Instead, is it right? Or number of rainy days is more important to rain.
So particularly for Markovian analysis, like for the further study of my topic, like
including in some other models. In our software, I mainly use the Markov model. So that's why I started with that.
What is the number of rainy days in?
That I did not calculate. I landed.
Yeah, I think this Dharmaburi district, within Dharmaburi district, there is a huge variation with respect to the rainfall, 1100. You cannot get, because some region definitely it will be dry, and some region they used to get a lot of rainfall. Okay.
Same surprise. Rice is also cultivated.
Oh, it is
as rainfall.
Like with the supplemental irrigation.
Supplemental irrigation.
In supplemental irrigation means
Like farm, like during now, like due to climate change, there is a lot of towns who are
Well water is mostly nowadays bore water, so many things are there. But this Marco, when it was released actually in this particular model,
1962.
is it not so old that because you have to incorporate so many factors.
Yes.
Okay. To say that this particular model can predict, you are telling that this particular season we can do this and that. There are a lot of, there are so many factors we need to add to make this model applicable for one district.
Yes.
You have to go still to narrow down the factors. So then only it can be applicable. Okay, good.
Thank you.
Well, huge impact. Some topics are already over, some are all undergoing. So these are all, in fact, it's a great opportunity to come forward, present it, give a lot of strength for you. All the best for all of you.
Thank you. Thank you for being here for from the organizing secretaries.
Great, thank you.
இல்ல அவங்க ஸ்ட்ரகிள் இருக்குங்களா அவங்க
On the AGSC, all really is not just a part, there will be struggle. Definitely, nothing you cannot get.
But எந்தெந்த ஃபீல்ட்ல வந்து ஷைன் பண்ண முடியும் அப்படிங்கறத அப்பதெளிவா சொன்னாங்க.
Huge challenge. But only thing we need to focus more.